Hi everyone, this is Jason, and in this project I built a machine learning model to predict the net hourly electrical energy output of a combined cycle power plant. And this is a real-world regression problem where it's important to have accurate predictions so that you can help power plants operate more efficiently and reduce fuel waste. And this helps by ultimately lowering emissions. And the dataset contained about 9,568 hourly observations of environmental sensor data, along with the corresponding power output. This is a supervised regression task because the target variable net electrical energy output, measured in megawatts, is continuous and known for each observation. To evaluate the model performance, I also used root mean squared error, or RMSE, which is especially appropriate here because it reports the error in the same units as power output, which is making it really easy to interpret in a sort of operational context. The dataset includes around 4 input features, which are ambient temperature, ambient pressure, relative humidity, exhaust vacuum, and these variables are physically meaningful and they do directly affect the efficiency of the turbine and power generation. There were no missing values in the dataset, so I could use all the observations without additional cleaning. I split the data into 70% training, 15% validation, and 15% test sets. And the training set is used to fit the models, whereas the validation set is used to compare different models and hyperparameters. And the test set is held out until the very end so that you can estimate the real world performance using brand new data relatively. And this helps to prevent data leakage and helps ensure that the model makes decisions that are unbiased. I started with a linear regression model as a baseline model. And on the validation set, it achieved an RMSE of approximately 4.56 megawatts. And then next, I trained a gradient boosting regressor, which is a more advanced ensemble method, and it's able to do nonlinear relationships. I also compared the two different of the gradient boosting regressions so that we could vary the different estimators and learning rate, and the configuration with the around 200 estimators and a learning rate of 0.05 performed the best. It had an RMSE of around 3.8 megawatts, which is a very big improvement over the baseline that we had previously calculated. Based on the validation performance, I selected the best gradient boosting model, and I retrained it using both the training and validation data combined. Then I evaluated the final model on this test set, and the RMSE of the test set confirms that the model does generalize well to unseen data and can give a sort of realistic estimate of how it would perform when truly deployed. To better understand this model, I examined the feature importance from the gradient boosting model, and the plot shows the ambient temperature is the most influential feature. After that, it's exhaust vacuum, and then pressure and humidity play smaller roles. And this aligns well with the real world thermodynamics of it, because it also increases the model's behavior and confidence. In summary, I built and evaluated multiple regression models, selected the best one using validation data, and confirmed its performance on a test set. This type of model can help power plants improve efficiency, reduce emissions, and support more sustainable energy systems. And I do hope that this can be used in the real world. Thank you for watching, and I hope you learned something new.